That work? Oh, yes. Hi, everyone. Welcome to the sixth IRES seminar for this semester. We are gathered on the unceded ancestral territory of the Musqueam Nation. I am personally a relatively recent settler on this land with a European ancestry that's tightly tied to France's colonization of Algeria. There's a lot to reflect on related to this and to the fact that I'm growing roots for my own children on this unceded land. Today, I have the pleasure of introducing our speaker, Ming Cao. Ming is a recent IRES MSc graduate, congratulations, supervised by Dr. Mark Johnson. She started her journey in China, where she developed a childhood fascination for plants, and that led her to study forestry at the University of Alberta. She then added on to that a passion for hydrology, and at UBC that led her to focus on studying water and energy exchanges in the soil plant atmosphere continuum. This summer she was a sustainability scholar, and she worked with the city of Vancouver on the integration of urban trees and green rainwater infrastructure systems. And that led to very practical recommendations on designing, constructing, and maintaining these types of projects. Last year, she was also the IRES Student Society treasurer, and she helped co-design a website for one of the co-secure initiatives. So that's a lot of great array of skills. And please join me in welcoming Ming today. It's okay.
Hello, everyone. Thank you all for your time. My name is Ming, and in the next 15 minutes or so, I will take you through my research, specifically on evaluating soil water dynamics and soil greenhouse gas emissions under climate smart agriculture. And this research was conducted under the umbrella project of a long-term research in the UBC farm. And before I dive in, I am aware that we're all enjoying this beautiful pumpkin season, and with the upcoming Apple Festival coming up at the Botanic Garden, it's the perfect timing to be thinking about something related to sustainable agriculture. I'd like to begin by thanking my awesome supervisor, Mark, and my lovely committee members, Sean and Yamuk, for their continued support and inspiration. Their mentorship has been a cornerstone throughout my journey, and I just couldn't have asked for a better team. Many thanks for Alan and Zoran for providing all the logistical supports, both in the field at the lab, and Dr. Andy for reviewing my thesis. Also, I'm so grateful to all the members at the Ecohydrology Lab. It feels wonderful to be part of this amazing lab, and I really enjoyed interacting with everybody. So the context of my research kind of speaks to the current trend of recognizing soils both as an important source and a potential sink for greenhouse gases, or GHG, with an increasing emphasis on quantifying key gas fluxes for carbon dioxide, methane, and nitrous oxide. There's a push across multiple disciplines towards developing sustainable practices, and many are investigating how different land management interventions can help mitigate the GHG emissions. The use of organic amendments such as biochar, compost, and manure is gaining attention in recent years. What's known is that amendment applications improve the soil structure and the fertility, but with varying effects on the GHG emissions, depending on the type and application method. And on another note, optimizing soil water management is becoming increasingly important in the face of climate change. While soil water content is a widely measured soil moisture indicator, it differs by type and is less consistent. Soil matrix potential, on the other hand, it offers a thermodynamic understanding of how water is retained and moves throughout the soil profile, which influencing the microbial activity and consequently the GHG exchange. And there is a need for more studies on soil moisture potential and greenhouse gas emissions. I'm going to shift gears a little bit. So soil water content refers to the volume or the mass ratio of the water to the soil contained in a soil sample. And the picture here is depicting for the volumetric water content. And moving on, this drawing shows a few key points along the moisture potential gradients and how it may affect plant growth. So if the moisture potential is too high, which is closer to 0, in this case, plants could suffer oxygen deficiency as well as root rot. If the moisture potential is too low, so in this case, soil becomes really, really dry, plants could suffer water stress as well as wilting. Echoing the current trend, I started with many research ideas in mind, but here to stay focused, I will just delve into one research question that's being discussed in my thesis, which is how do changes in the GHG fluxes follow changes in soil moisture, which could be caused by irrigation or precipitation? And in other words, I'm interested in learning the temporal interaction of the soil GHG fluxes with soil moisture during different drying and wetting cycles. Moving on to study design. So the study took place within one field at the UBC farm. It was a random block design with 4 soil treatments distributed in 3 blocks. The picture here shows how subplots are arranged together, and you see the lines in gray on the outer surface. It depicts the ongoing complete experimental extent of the larger research project, which has been established since 2017. And here on the corner, on the left corner, the legend says edit or control. It refers to whether soil amendments targeting high nitrogen mineralization were applied to plots. And the term targeting high nitrogen mineralization refers to enhancing the breakdown of organic nitrogen into inorganic forms that would be more readily available for plant uptake. And rye clover, polyculture, or fallow just refers to the type of cover crops that is planted during the shoulder season. And here it shows the succession of the crop stages during the measurement period. The data collection spanned between April to October last year. April to May was the shoulder season. It's growing cover crops. And in June, these cover crops got harvested and left as crop residues. The soils were tilled twice. Amendments were also applied. From July to October, it was the main growing season. Some brassica seedlings were first transplanted to the field and left until maturity. There was also sprinkler irrigation happening, in addition to natural rainfall during the main growing season. And here is a summary of the instrumentations used for the study. So for soil water, we had 5 TM volumetric water content and ensemble soil matrix potential sensors, both installed at 8 centimeters soil depth. For GHG fluxes, it was measured through an automated soil chamber with a Picaro gas concentration analyzer, all designed by Zoran. And I obtained the weather info from a nearby weather station at the totem field. And I also obtained the vegetation index from some satellite imagery data and calculated NDVI. So these pictures are just for background. For example, the mean daily temperature during the measurement period was about 15 degrees Celsius, and NDVI was around 0.8 during the cover crop shoulder season. I used cross-correlation analysis to understand how gas fluxes responded to the drying and the wetting cycles. And the purpose of this method looks at the correlation between two time series, so x and y may be associated with the lag values of x. Essentially, we're trying to understand how one variable moves in relation to the other over time. And the cross-correlation coefficient, they range from -1 to +1. The magnitude and the sign of the coefficient values at any given time lag analyzed, they provide insights into the strength and direction of the relationship between the two time series calculated. And here I'm transitioning to the results section. So this graph is showing the cross-correlation of GHG fluxes with soil mixture potential during a rainfall event in early May 2023. The horizontal axis depicts the time lag in days, and the vertical axis is showing the cross-correlation coefficients. The dots in red just indicates if the correlation was significant. I went with the compromise of using the temporal resolution in daily interval instead of the original 2-hour interval, because when I did the data cleaning, the noise to signal ratio was too high. And I can walk you through this graph a little bit. So if we focus on the top left corner, so this facet, which is directly under the CH4, you can see the first 3 dots are depicted in red, and it's showing a decline trend from positive to negative values. And this means the higher methane fluxes under the added polyculture treatment in this case is positively and significantly correlated with higher soil water availability from 0 to 3 days ahead of time. And in short, the soil GHG fluxes were mostly synchronous with both of the soil moisture indicators I analyzed in the spring-fed condition. And the overall soil moisture memory lasted about 1 to 3 days within the system. And this is another scenario considered, which I selected a frequent wetting and drying cycle under irrigation during July 2023. And in short, there was no time lag observed for methane fluxes with either the volumetric water content or the mixture potential. Soil moisture from 1 day before was significantly and positively correlated with the CO2 and N2O fluxes under certain treatments, such as added polyculture or control polyculture. Speaking of the study implications, theoretically, the results extended the established knowledge of the GHG fluxes to soil wetting and drying conditions by providing a field setting in a temperate climate. Although I didn't show in this presentation the principal component analysis and the random forest models I did also confirmed soil moisture as a crucial indicator for impacting the soil GHG emissions. And practically speaking, in the future, well-planned irrigation could be useful for help mitigating methane and N2O emissions by facilitating conditions that discourage methanogenesis or N2O production. And my thesis also shown that local farming in this region could prioritize for reducing carbon dioxide emissions. I confess there are research limitations. I'm glad to know there's always more to learn. So for example, the characteristic of this study was a passive monitoring at the field scale. the data spanned primarily the summer months of 2023. All the analysis was empirical, and the time lag, the temporal resolution was evaluated in daily intervals. For future considerations, I think it would be interesting to see the interannual patterns for the gas fluxes and explore some active soil moisture manipulations. And I know any modeling that they range from a spectrum where it could be purely data-driven to purely based, so process-based. I guess it would be good to incorporate some soil water hysteresis phenomena. And finally, to consider the trade-offs between GHG emissions and crop productivity. I guess I'll stop here. Thank you all for listening. So the question was, is the reduction in fluxes related to soil drying out? And I think it depends on the type of gases. I know for methane, the reduction of, well, like the drier the soil becomes, it actually reduces the methane emissions or production. For N2O fluxes, if you keep the soil water content around 60% or above, and you keep, how would I say, like fluctuating or alternating between drying and wetting frequently, this condition could be optimal for improving the N2O emissions from the soil to the air. And for carbon dioxide, I guess there is no consensus so far, but I would assume in my case, for example, I guess this one would be easier to explain. If it rained and it lasted for a couple of days, it starts drying out, I would say most of the time carbon dioxide is increasing, it's coming back. So if you have more rain or is wetter, it's for prohibiting carbon dioxide, how do I say that? Coming out of the soil. I hope it helps. That one, this one. Oh, actually, this picture, this calendar graph is showing the data availability I got from the satellite imagery for calculating vegetation index. I guess for rain events, you're gonna look at this middle panel here. So you said it's around mid-May. It's pretty dry, I guess. Last year was a bit weird. There was a lot of rainfall at the end of April, and June, from what I remember in the field, it was the hottest of the year, and it barely rained. And well, there's no irrigation showing in this plot, but for precipitation, we got several rain events occurring after, I would say, July. And the rain season just came back around October and late September. Thank you for your question. That's a good question. I guess to repeat, from the gas analyzers, which gas flux has the highest emissions across the field I measured. So for the data analysis I did, I guess like over 96% of all the emissions, only considering the magnitude over time, was dominated by carbon dioxide. Even like the global warming potential of nitrous oxide and methane are way higher than like typical carbon dioxide. They don't compose like a huge percent. This could also be the way Picaro gas analyzer measures the gas fluxes, is that it doesn't tease out certain components for carbon accumulation from cover crops, from like the crops you're actually growing. I guess it captures like a confluence of things. So the carbon sources could be from the nutrients added to the soil. It could be from some of the crops growing, and they get captured in these large chambers I was measuring at a certain time period. I think I acknowledge this measurement limitation. And I guess to the other question you're asking, what causes the methane to be emitting out from the soil, right? I think in my literature review, methane is very well studied in paddy soil fields, so more like wetland based. And this apparently is an upperland field study. It doesn't encounter those saturated soil conditions that often compared to a constantly submerged rain-fed or water-grown fields. I would assume it's because of the soil moisture. There are dry periods over the measurement times. Interesting question. I just never thought it would be asked in a way. So the question was, would there be any implications from this study related to the broader policy implications related to infrastructure, particularly for like agriculture? I think from a policy perspective, no, let me start from the farmer's perspective, because I would really want to understand at what cost farmers would need to sacrifice to lose their productivity, to be able to have less soil emissions. I think in the sense of you want to have more crop yields, it's good to take consideration of the soil water management, like the co-benefits of reducing water, but also not compromising too much of the yields. Or if this goes to the policy, I think increase the investment in similar research and figure out the optimal soil treatments that's suitable for the BC context, and for Anything with infrastructure? Are you saying like the I see. I think this is a passive monitoring study. When it rains, we get measurement, and when it's like pretty sunny, we also get measurements. Um, the soils didn't get that dried out, so our data didn't span like the whole soil water profile as it could be in an ideal soil graph. But for infrastructure, um, I talked about this a little bit in my discussion, and I guess one method I suggested was to irrigate more intermittently. If you have enough infrastructure or on timely monitoring, it would be really nice to know ahead of time how much is gonna rain or how much irrigation you're gonna apply, and then control the soil water saturation to an optimal point, tailored to the specific fields you're growing the crops. I guess that's the best answer I can give so far. Sorry about that. Conventional treatment. I see. So the question would be, what would I expect to see if if there's an additional treatment that's very conventional, it's intensively managed, and how much gas GHG emissions that would come out compared to these more, I guess, climate smart treatments. I actually compared similar studies from other parts of the world that's also doing agricultural GHG emissions. And what I found is, in terms of methane and nitrous oxides, these two gas fluxes from this specific field are towards the lower end compared to all the studies I found that did somewhere else. I guess it's a good thing, but also because they composed a very, I guess, little percent of the whole emissions profile. For carbon dioxide, um, the the values for, well, even for the control fallow, like you do nothing on the field, you don't apply any amendments, and you leave the field empty during the shoulder season. This actually gives the least carbon dioxide emissions comparing to within these 4 treatments I looked at, but comparing to other similar studies, this one is towards the higher end. And I suspected this could be because the measurement methodology, it didn't tease out some of the potential carbon sources that entered the ecosystem. Cumulative emissions. Oh, I see. So the question would be, for if not looking at emissions at any time snapshot, the cumulatively, would it also emit less to the atmosphere if there are more water applied? I guess I've only looked at the cumulative emissions when it's frequently irrigated. So in the main growing season, I didn't compare it to another scenario, like say it was cover crop, it didn't manually irrigate the fields. I cannot answer that question, but within the cumulative emissions I looked at, the results were very similar to the question Caleb just asked. I got the lowest cumulative emissions from the control fallow treatment as well. So this question is for amendment applications, what's the timing, and was there any consideration of the rain events like before and after the application? Whether the choice of the application dependent on the raining. The amendment was applied in late June, so it's in this soil stage. After soils were tilled twice, after the cover crops residues are left on the ground for about a month, and I think it was an extremely dry period across the whole month. There was no rain during the application. The ground was pretty dry. Thank you very much.